computer. Good day, good morning. This is our EASY lecture series recordings. Today is Monday, July 6th. We're all in Davis. I'm in the attic of my house, and Mr. Han Yang is in his apartment, Dr. Han Yang.
Hello.
And Dr. Heshan Wang is in his apartment. And today we are going to talk about calibration of simplified yet very well simplistic but refined sophisticated model for modeling of sand. So Heshan, I need to allow you to share screen. So please go ahead and share your screen, and we'll start.
Okay. Yeah. Calibration. Okay. Can you see my screen?
Yes, thank you.
Yes. Okay. Yeah. So yeah, thanks, Professor, for introducing me. Yeah. Today we will continue our talk on the calibration of the elastoplastic model for the sand, and yeah, as we discussed in the previous lectures, that we can for engineering practice, we can model the elastoplastic behavior of sand using a simple yet very powerful model called hyperbolic drag-plug model with a non-associated plastic flow and Armstrong-Frederick rotational kinematic hardening. So today we're going to talk about how do we calibrate the parameters for such a model. So for example, let's say in engineering practice, you have for a given sand, you know the density is like 2,000 kilograms per cubic meters, and you are given the shear wave velocity. The shear wave velocity is 200 meter per second, and the P wave velocity is 375 meter per second. And also you given some strength parameters, the cohesion like 20 kilopascal, and also the friction angle is 36 degrees. So how do we calibrate our model based on this very limited given parameters? So first of all, we can calculate our elastic parameters of the model using the equations from the elasticity. So essentially, we can calculate the Young's modulus and also the Poisson ratio from the shear wave velocity and the P wave velocity. We can calculate for this material, the Young's modulus is around 203.2 megapascal, and the Poisson ratio is around 0.3. So, so this is for the elastic parameters, and then for the other parameters, and because the sand is pressure dependent, so when I do the calibration, I usually will choose a specific depth, and then I will calculate the target shear strength of this sand at that specific depth, and then I can calibrate my parameter to match such a target shear strength. So, for example, here we have been choosing the depth at 10 meters. Then we can calculate the confinement or the pressure at the 10 meters is equal to the depth 10 meters times the density times the gravity was equal to 196.2 kilopascal. And then based on this pressure, we can calculate what is the expected shear strength of this material at this depth using this simple equation, which will give us around the target shear strength is around 165 kilopascal. So this is a very important number that we're going to match to calibrate our model to match such a value.
And
so,
if I may add, I mean, you can of course do this, and you can check. You should check, and you'll show this, I think, later on. You check at different depths, and you make sure that it makes sense. Yes.
Yeah.
Thank you.
Yeah, that's true. Yeah. And then, so this is the real easy DSL that you can use to model such a sand, and we have 11 parameters for this model. And you can see here the first 3 parameters. So we already determined them from the elasticity, the elastic parameters, and then the parameter called friction angle. We set a very small value here, as we discussed in the previous recordings. We will use a very small elastic region, essentially a very tiny drag-plug cone to model the elastoplastic behavior. Essentially, we will have the small cone will rotate along with the evolution of the back stress, so that it can still have the pressure dependent behavior. But we will set up a tiny cone. So we will choose a very small value for the friction angle, which is 0.01. Yes, Professor. Yeah. Professor, you are muted yourself. Professor, you are muted yourself. Hello, Professor. I think you are muted yourself.
Yes, I did mute myself. I'm sorry. So we use this name friction angle for historical reasons. In fact, it's supposed to be this big, but right now we actually do rotational kinematic hardening. So it's going to rotate, and so this is really not the friction angle. This is just the size of the opening of the cone, and it's very small. And that's a trick that
Yeah,
we learned from the Farias, from his models. All of his models are very tiny cone that rotate in stress space, and so this is the same trick here. But you eventually get the shear strength and the friction angle as an ultimate displacement or rotation of this cone by using
yes.
Armstrong Frederick. So yes, go ahead, please.
Yeah, yeah. So we will just set a very small value here, which is 0.01, and the cohesion value you already be given, which is 20 kilopascal. And there's an additional parameter called rounded distance. So this parameter will control the hyperbolic rounded part of the yield function. As we talked before, usually we will set a value that has the same magnitude of the cohesion, but a little bit smaller. So we will just choose 10 kilopascal here as the rounded distance. And then there's a two parameter, which is quite important, which is the Armstrong-Frederick HA and Armstrong-Frederick CR. So these two parameters, we're going to calibrate them to match the pressure-dependent shear strength behavior. So initially, we will just set it as a 3 megapascal for HA and a 25 for CR value. And then for the isotropic hardening rate, as I mentioned before, so for the modeling of the soil, we find the isotropic hardening is not that useful and realistic. So we will not use any isotropic hardening here. So we will set it as a 0 kilopascal. And then you have this parameter, which is the initial confining stress. So this is the parameter to specify the confining stress for this material. Since for most of the modeling and simulation in earthquake soil structure interaction, we're going to have two loading stage. We're going to apply the confinement, have a self-weight loading stage to apply the confinement. So when you define the material, you you should not apply any like pre-existing confining stress. We will do the apply the confinement through the self-weight loading stage. So for now, we will just put a very small value, let's say 1 kilopascal for this material when we define this material. Yes, Professor. Yeah.
No, just a note. So this is really the reason for this parameter was when you have a non-cohesionless material or cohesionless material that one, let's say regular Drucker-Prager that has this tip right at the start of the stress space.
Yeah.
You don't want to be at that point, so you need to be a tiny bit inside. So we put this as a tiny bit inside just to help the system, but it's going to go through through equilibrium iterations, and it's going to end up where it goes. So a small
Yeah.
value, 1 kPa, is works really well.
Yeah.
Go ahead, please.
That's true. Yeah, and then you have this final two parameters, which is the plastic flow Xi and the plastic flow KD, that will control your non-associated plastic flow. And if you want to calibrate these two parameters, actually you might need to additional information. For example, you might need to do some triaxial test. You need to have some stress strain response to calibrate these two parameters. So to calibrate these two parameters. So for engineering practice, if you only have the cohesion and the friction angle, actually you do not have enough information to calibrate. So for now, we will usually we will just keep it at 0, which means your plastic flow is a pure deviatoric. Yes, Professor.
So these are really important if you have a coupled system where you have volume change. In our case, volume change might not be that important. It's a dry system. If it's confined deformation, the volume change will be important, but you need, as you said, you need additional information. You need the volume change information, volume change
Yeah.
data. So
Yeah.
thank you.
Yeah. So yeah. So if you do not have this information, we will just put 0, which means you need to know that this is a pure deviatoric plastic deformation. Yeah.
Yes.
And so with this initial set of the parameters, then we can apply the confinement at the pressure with the pressure at the 10 meters depth that you were calculating before, and then we can do a simple pure shear test, and this is the stress strain response we can get. As you can see here, remember our target shear strength at the depth of 10 meters is around 165. So we are a little bit lower than the target shear strength. And also, if you want to check, the stress at the 1% strain level, as we mentioned that, we generally want to expect it to be around half of the shear strength. So this material is a little bit softer. So based on this, we want to, if you do the calibration, you want to increase your HA a little bit so that you can have a higher, shear strength, and also your stress strain response will look a little bit steeper. Your soil will be a little bit stiff. So then after some fine tunement, you can change this parameter HA and the CR. You can get this fine-tuned response with HA equal to 4 megapascal and the CR equal to 32. And you can see here now we can match we can hit the target shear strength, and also the stress strain response looks reasonable. And then for the calibration of the sand, it's always very important and good to check whether your material is pressure dependent. And remember, we are doing our calibration based on the pressure at 10 meters. So it's good if you can change it. You can check the pressure, the shear strength at another depth from your calibrated parameters. So now, here I'm checking again checking the shear strength, the stress strain response at another depth, which is 20 meters. So as you can see here, when our depth doubled, essentially our confinement doubled, we also get almost a doubled shear strength response, shear strength response. So this is
Yes.
pretty good and it looks reasonable. Yeah.
Yes.
So yeah, with that, you already finished your calibration of your sand, and you can look up more information in this reference. And also, finally, we want to give thanks to our collaborators, the funding resources and agencies, the collaboration with these funding agencies, and eventually you can look more information to our Real Easy website. Yeah.
Thank you very much. So if you'll stop sharing your screen, we'll conclude here.
Yeah.
So Heshan, just click on yes.
Yeah.
So we'll conclude here. This lecture will continue with next set of lectures, and I thank you and hope to see you back. Thank you. Let me stop
Yeah.
recording.